Hi, and welcome to the Control Engineering webcast, Overcoming Big Data Challenges in the Industrial Edge, sponsored by Emerson. I'm your moderator, Gary Cohen, and I'm happy to join you today on behalf of Control Engineering. So here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, just refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast or the volume of my voice by adjusting your volume on your computer or by adjusting the volume on the webcast platform. If you're having technical problems with audio or the slide presentation, just click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, simply type the message in the Ask a Question box and someone will get to you as quickly as possible. So if you have questions for our speaker, you can type those in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded, and you'll receive an email within a week with the link to the on-demand event. Once we're done here, to download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. So you've already probably heard enough from me, so let's get to the reason why you're here. I'm happy to introduce today's distinguished presenter, Richard Carpenter. Rich is the Executive General Manager of Product Management for Emerson's Machine Automation Solutions business. He joined the business in 2016 and drove a shift in direction to focus on industrial edge systems, which are securely and natively connected edge controllers and edge computers. The business is in Charlottesville, Virginia, with worldwide distribution and deployment capability for their control system, operator interface, industrial PC, motion safety, and IIoT products. Prior to this position, Rich was the Chief of Product Strategy and Chief Technology Officer for GE Intelligent Platform Software and Services business. He led GE IP's overall portfolio plan, the technology direction, and the initiatives to converge software and controls across GE. He worked extensively with other GE businesses to establish the requirements and vision for the Asset Performance Management Cloud platform as part of their digital transformation. Rich has multiple patents in his name and a strong track record of introducing new first release products. He began his career in GE's Edison Engineering Leadership Program. He's earned the GE CEO Leadership Award twice. He attended the University of Illinois, graduating with a Bachelor of Science degree in Engineering and a Master of Science degree in Computer Science from the University of Virginia. Rich resides in Charlottesville, Virginia. Thanks so much for joining us today, Rich, and I'll hand things over to you.
All right. Hey, thanks a lot, Gary. I sure appreciate it and appreciate the kind words. Listen, I am very passionate, as Gary said, about the edge. It's an area that I think is really on the verge of the next generation of productivity across all of the way we do manufacturing and run infrastructure projects. And so, we put a lot of thought into this, both from a product standpoint and a strategy standpoint, and really even helping our customers think through what it means for them. And, there's a number of common operating challenges that we see companies face. To a large extent, the ability to drive further efficiency is hard right now because we've used the same set of tools for the last 20 years, and those tools have been great, but you start to reach the limits of capabilities in terms of extending your performance with just traditional mechanisms. That coupled with the fact that we're going through a fairly good demographic change right now with a change in the workforce, a lot less experience, a lot more reliance on digital techniques, and you really need some different ways to drive operational efficiency improvements. Still too much downtime. Part of that is a result of equipment becoming more complex, coming in from different vendors, the people on the floor not necessarily having as much experience with that equipment, and really being used in a way that isn't always as intended, meaning far more frequent product changeovers, much smaller runs from a production standpoint, and really, a need to keep that equipment running better and longer, but not necessarily having all of the expertise to do that. A big problem can be products that are out of spec. And if you don't error-proof a recipe, for example, and you don't get the ingredients quite right, you could throw out an entire batch of product as a result of that. Those are the kind of things that you have to be forever vigilant about and making sure that you're creating a production environment which is as error-proofed as physically possible. And then today, ourselves included, and many of our customers really, sustainability is important. Reducing the carbon footprint is important. Understanding energy consumption and potential waste is important. And so having ways through edge-based applications to understand better your energy footprint, to understand where it could be optimized and take steps is a critical need that we see that's out there, and something that we think about, just from a corporate governance standpoint as a very important initiative across the board. Look, there's a number of reasons why some of these things are tough. The machine visibility is often limited. And I'm going to talk a little bit more about that in some subsequent slides and how we address that. But when you don't have visibility to the machinery and you don't understand its condition, it's going to fail more frequently than you would like to. And when people have very big, expensive equipment that has a very high cost of downtime, they tend to put a lot more maintenance and service into it, even sort of when it's not needed. But when the equipment seems to be of lower value and you run it to failure, then you end up with this condition where you're reacting to things that have happened on the floor. And so what you want is improve that visibility so that you understand the condition and are relying less on schedule-based activities and more on condition-based activities. We all have had large data collection initiatives for many, many years. Historians is a market segment that emerged as a result of that. There's data warehouse initiatives, in prior generations, data lake and big data initiatives that happen today. But I think a lot of people find themselves in a sea of data without really an ability to make the best use of that data or to get the promised insights out of it. And part of this particular presentation is oriented about rethinking those big data initiatives so that it's more based on known problems and known solutions and things that you can get immediate benefit for as you grow your way into the more insight-driven analysis based on correlations that you weren't expecting, which is what you would get from a big data environment. As I said, sometimes we react to failures that have occurred, and then we try to marshal people as fast as possible to prevent those failures in the first place. And if we can get to the point where from data collection, especially at the edge, we can get early warnings of potential failures, now all of a sudden we can take proactive action based on historical information and insights from the data and really avoid a lot of those reactive-based maintenance processes in the first place. And all of these issues above can lead to customers who are not quite satisfied with the product. They don't always understand the root cause. I frequently see OEMs on one side that deliver a piece of equipment, it gets used in a way that they weren't expecting or even normally. A customer on the other side that gets this equipment, the equipment goes down far more often than it's supposed to. It doesn't hit the production goals that were published in the specifications. And the two sides, because they're not sharing the same data view of those events happening, tend to sort of butt heads and not solve the core problems that get us to a more productive environment. And so we think some of the things we'll talk about today are oriented around that problem as well. As you solve edge-based processing and have information and insights that can support both OEMs and manufacturers, both sides can actually get a better result. So we'll talk a little bit about that as well. So what does it mean? We talk about little data. Start your big data strategy with a little data approach. And really what we mean by that is, don't try to solve all of the data collection into a single environment and expect to get instant insights out of it at the beginning of the project. Start small and prioritize. Figure out what areas of the plant have the most potential for benefit. What are the known problems that you want to solve? And then initiate some data collection and analysis close to those problems so that you can solve those issues through visibility and analytics quickly and locally, and sort of get the experience around managing data close to the processes. And I think what you'll find is as you're collecting a series of small data, little data projects and doing those analysis, it puts you on a journey to be able to collect and analyze the full data sets and really get a lot more benefit from it in the end. So first, start with small chunks, break the plant into small pieces. Use edge-based architectures, which we're going to talk about more, to operate close to the plant. Have an environment where that data can flow to a big data type analysis so that becomes possible down the road when you're ready, and build on that collection of little data to get to your big data initiatives. We think that that combination is actually going to get your results faster and stronger than you would if you start the other way around. I think, what I've personally experienced is if you start the other way around, there's a little bit of a hope that once you have all of this data in one place, the insights are just going to pop out at you. And because you're dealing with a different group of people, more in the data engineer category, the data science category, and then you have to bring in a domain expert, it actually is a much bigger effort to get the insights, as great as they are, if you start with the big data environment. So this is what we mean by, approach big data from a little data standpoint initially. So just a little bit more on that. A big data initiative goes through a pretty well-defined process. You identify some problem that you want to get more insights on. You design some experiments, set those up, perform the experiment, and reiterate until you get the information that you want. You validate the findings are actually giving you something useful. You take some action, you manage changes, and you capture the impact and repeat the process wherever it makes sense. And this is a great process, but as I said, it requires multiple domains to manage, and you're dealing with potentially petabytes of data versus smaller amounts of data that's close to the machine. And with little data, you can start close to the field devices, maybe even instrument equipment a little bit stronger than it is traditionally. And that's one of the keys to the edge initiatives that we'll talk a little bit more about. From that edge device, you get better visibility into the equipment, far more than you could get from just the traditional control and SCADA system, which is the way we've done it for the last 20 years. From that, you can make some pretty quick decisions that are actionable, and then start to scale to 2 machines, to 5 machines, to a line and on. And before you know it, you're getting some of the benefits of the full plant view, even though you've started sort of addressing it one problem at a time, one insight at a time, one analytic at a time. So it's pretty key to be thinking about getting the benefit early to sort of get confidence in your data initiatives and that you can find ways to get value. I'm going to look at it from the standpoint of OEMs and end users, manufacturers, for example, plant operational personnel. From an OEM standpoint, the primary thing that we see OEMs trying to do today is build competitive advantage. More and more OEMs are looking at industrial IoT-enabled equipment out of the box as a way to differentiate their equipment versus somebody else's equipment, while simultaneously providing a piece of equipment that provides more value to the end customer. So for example, in traditional machines, the OEMs will spend enough money to get the control system in place to properly operate the machine at spec, and not any additional money to make it easier to diagnose, or to make it easier to go through changeover, or to make it easier to understand the performance over time. And that's what's changing. By IoT enabling a machine through edge-based architectures, now all of a sudden machine health and performance levels become a natural part of that application. And they can be done independent of the way the control system operates, so that you can extend these over a continuous period of time without having to open up PLC programs, add additional I/O points just for control or to pass through the control system, or even from the SCADA system standpoint. And that gives us an ability to provide a better experience to customers, but also potentially deliver new service models. If you've ever wanted to try to get to an as-a-service model, you need that data collection and those insights to be able to deliver that reliably to customers. Now, a lot of times, as I said, the OEM's equipment is used in ways they didn't expect, and then the end customers have failures that they don't expect. And really what they're trying to do is not necessarily improve that specific piece of equipment. They're trying to get productivity gains, build more product faster with higher quality and better results for their end customers. And so the end user manufacturer's goals are a little bit different. They're oriented around making money through the products that they deliver, avoiding any kind of recalls, avoiding any kind of returns, and really optimizing the decisions of the operational people in order to have the best result for their end customers. And when this is working well across the two, and the OEMs have visibility to be able to improve their equipment, and the manufacturers are getting the benefit of these additional diagnostics, it completely changes the relationship between the two groups to be one of how do we evolve this capability together so that it meets my ever-changing production needs, especially with users that want more customization and shorter runs, and the OEMs can build better equipment that's more differentiated. So edge-based analytics, edge-based architectures are really key to making this happen. Now, we have an edge maturity model that, if anybody wanted to follow up and get more details on, we'd be glad to talk to them in separate discussions. But customers typically have a number of stages that they go through. And at the far left side, in many cases, there are still islands of automation. That is equipment that is operating. Maybe it has a local HMI that somebody can interact with, but it's not necessarily even networked where you can understand its health and its performance as soon as you walk away from the equipment itself. And so islands of automation do still exist. Sometimes a plant can be highly connected, but still have some equipment that is islanded. And if you can't see it and you don't know its health, it's going to surprise you, no question about it. Many people are in this connected automation stage, especially for an automated factory. That's what PLC, DCS, SCADA systems have done for many, many years. You even hear, people talk about the connected enterprise and this type of thing. That's, I would say, what's evolved for the last 20 years. That's state of the current manufacturing processes, plant processes that are out there. We think that world is changing very, very rapidly, and just thinking about it from a connected automation is not enough. Sure, you can see everything, but what you see is limited to the information that was available in the controllers, the PLCs, the DCS systems, and the SCADA systems, which are very much oriented around current production, not additional information that allows you to make better insights and get those analytics that make you support a step change in operational efficiency. And so this border is what you have to cross in order to get to what we view as the current state of the art, really the next generation wave of where people are going, and that's enhanced connectivity and analysis. And the big difference between these two is through edge architectures, you start to bring in information not available traditionally in the control systems architecture. And a lot of times you do that actually in parallel and independent of the control system. So for example, we'll talk about edge devices. An edge device can be connected to a piece of equipment that's actually running in the plant. And it can also be connected to the new generation of smart sensors that are available for a variety of different applications. The combination of what's in the controller and what's available through these additional sensing techniques can give you a set of analytics that actually is just not possible with traditional methods in the connected automation, the standard enterprise. And why do you want to do that? Well, where we want to all end up, and eventually the industry will get there, is more insight-driven operations. And what is insight-driven operations? Well, there, the operator, based on the data that's been collected, the historical performance, the analytics that are running, when an event happens or is about to happen or may happen at some point in the future, is going to get information that says, hey, we see this event building. And that event typically leads to this problem. And this problem can be prevented by this set of steps. And there may even be a digitized workflow to take those steps. And really in the insight-driven operations, confidence intervals, if you take this step 80% of the time, that's going to fix the problem, is where you start to get to. And that historical information and the analytics that it's based on is really what gets you to that next level of productivity in the industry. And so we encourage all of you to think about where you are on this edge maturity model. Understand you need a new edge architecture to cross this boundary. And once you get to this boundary, the next step is that enhanced connectivity and analysis. And that's your first step to get to a more insight-driven operation. So what does this mean? I'll just give you, some quick examples. So little data collected at the edge, enabling some optimization from the source. Well, what if your OEM equipment had an edge architecture that's part of it and delivered OEE out of the box? Just as an example, overall equipment effectiveness. The machine is delivered with an edge analytics that quantifies failures, quantifies performance, quantifies what people can and should do in order to get that application up and running faster. That's the way you have to start looking at your equipment, is that it's delivered, IoT enabled, based on little data-based applications, and providing new analytics that provide more benefit to the end customer. Same thing with energy efficiency and sustainability. So what if the equipment is delivered or the manufacturing facility is monitoring all of the consumption, whether it's power or water or other applications throughout the facility from a little data standpoint, and that's used to identify where improvements could be made. And I'll show you an example a little bit later, but a simple one is in a pneumatic-based application. It's all based on compressed air. That's running a machine and the motion capabilities associated with it. And if your little data analytic is telling you that to get the same result, you're having to put more and more air pressure into the system, you now know that you're consuming more energy, which is waste, than you would otherwise have to, and you're being alerted to the fact that there's a leak in the system somewhere. That's going to help your sustainability initiative. It's going to drive efficiency by reducing your overall cost, and it's going to give you a more sustainable facility and connectivity. Then finally, because we're not islanded, a little data initiative doesn't mean that that's the only consumer of the data. We still want you to enable the big data capabilities that you strive for, to look across the plant or even to look across multiple plants. And so from that standpoint, you need connectivity that is flexible, that is secure, and that is based on open standards. And why is that? The consumers of the data might be traditional OT applications. Maybe it's going to a historian or a SCADA system. They might be a new generation of IT-based applications that are doing more advanced analytics in a different environment, maybe a much higher compute capacity environment. Or it might be sent to a cloud tools. There's a great set of sort of emerging analytic capabilities using machine learning, artificial intelligence, and others that are being provided by default through the cloud providers. And these new edge architectures actually need to be able to bifurcate the data to all three of those potential consumers of the data. So I like to think of, the past 20, 30 years as being sort of the way the Purdue model forced us to operate. And that today, the applications allow us to completely blow up that model and be able to take the data from its original source and share it directly to the consumers of that data without having to go through all of these network layers of the past. And so I really think that those architectures are here today, thanks to the edge, and those are the things that you want to be thinking about in your own initiatives. So, how do you get there? Well, I think the first thing I mentioned before is break the data into little chunks. Look at the entire plant. Where are the data sources that are available to you, and match that with the priority of where the biggest opportunities are to get benefit. And start there. Start in those applications. Put your edge architectures in place, connect into those data sources, bring in your domain experts, and through a combination of the little data that you have and those domain experts, put the analytics in place that allow you to get insights right at the point of use. Sometimes you have to do that anyways, to be honest with you, because sometimes that data is very high fidelity and you just can't afford to bring it to a cloud type environment. Maybe you're sampling data for the cloud. Maybe for this type of application, you need to look at second that's, more than 1 hertz in terms of availability. Second, you can't live in a partially connected world for some analytics. You want to be close to the edge so that independent of whether there's connection outside of the facility, you're still collecting the data and you're still running the analytics to help the operators. You can always use store and forward techniques on an edge processor to get the data offline whenever it's reconnected. And then you want an architecture that's scalable. So as you start with one data source, and then you bring that to the second, to the third, to the fifth data source, you really have the ability to scale that and scale that quickly. So now let me talk to you a little bit about what an intelligent edge platform looks like and what kind of capabilities you want to expect from those platforms. Emerson has put a lot of effort into this perspective, because we've thought of the problem a little bit differently. It's not just edge computing, which is a critical part of it, especially for a installed base that's already established, but it's also an edge controller that brings the benefit of edge architectures and traditional control architectures into the same physical presence to do things that neither could do independent of each other. And so I want to talk about sort of the combination of what you should expect from the software and then different deployment architectures that make sense depending on the need of the specific application. And a couple of things that you want to be sure about is, one, that the architecture is scalable. Scalable means two things. Scalable means you might have a very large number of small edge processes spread out throughout the plant, and you want to be able to manage that centrally so that you don't have to physically walk around to the different places in the plant to access them, to change the application that's on them, to start and stop them, et cetera. The second is that it's flexible. Today's customer of an edge-based application architecture is not just the traditional OT folks. Sometimes it's the OT community, and there should be a set of tools that are friendly to that group. Sometimes it's the IT community, very familiar and competent in the do-it-yourself environment. There should be a series of tools that support that group of people. And some might be people that spend their life working in the cloud and just want to get the data off as fast as possible, route it from the device up to the cloud where they can use a set of familiar tools in a elastic compute environment to do very, very broad analytics. The third is it has to be open. Nobody has any patience for closed protocols anymore in today's environment, and the different communities have different favorite standard protocols. On the OT side, OPC UA is probably the most popular for this type of application, but MQTT is very popular in the IT community, and sometimes used across each other's environments, but those are very open protocols, very suitable for this type of application. Some people just want to get it into a standard database, because the database has a standards-based interface, and once it's there, you can access it through standard queries and make use of it. So that openness is very, very important. And finally, and I don't want to belittle this aspect of it, the security is absolutely critical. If you're starting to put additional compute processing close to the equipment in the plant, and that is securely communicating to other applications, maybe in an IT servers or even in a secure cloud environment, you want to make sure that the edge applications have a secure path from the beginning to the end and are using the most recent secure techniques to do that. So these are sort of hallmark requirements that you would expect in an edge platform. We think of it in terms of a set of capabilities that are required. First, you need to be able to administer the IoT devices. So I need to be able to sit centrally and be able to see what IoT devices I have. I need to be able to make changes to those devices, and I need to be able to push those changes out or make those changes from that central locations. Second is I need a rich application development environment that supports both those IT and OT, as well as the cloud use cases, through a set of well-known applications that the community already knows how to use. And that's a very critical aspect of this. Here I'm showing a graphical tool for creating the logic that's running actually on the edge to be able to interact with operators, run analytics, or even produce dashboards. You want to be able to start small, but then scale to many devices. Some of your edge applications are at different points in the architecture, because edge is exactly what it means. It might be edge next to a piece of equipment, it might be edge next to a SCADA system, it might be edge next to one of the plant systems, and you want to be able to access the data and do something with it from there. Security, we talked about a couple of times, really critical. And then it needs to be open through the most commonly used interfaces. So given that, we have really thought through a core set of services that need to be available in an edge platform in order to support, as I said, bifurcating the data and running local applications so that it can go to the consumers as well as support the local processing. And you need to be able to do both. If you're going to start with little data in order to drive big data initiatives, you're really sitting down in that edge device and you're running a IoT-based application to get local insights. However, you want to be able to push that data up to the cloud gateways into the cloud applications to support your big data initiatives. You may want to put it into a historian or SCADA or maybe inform an MES that a certain operation has happened. And you may want to use it for remote monitoring and diagnostics or more plant level optimizations to look at, is the flow of material through the plant as optimal as it could be? If I have 10 machines of the same type, are they all operating at the same performance levels? And really get a broader set of analytics across the different equipment. And that needs to operate in a kind of embedded platform that's easy to manage, secure, and allows you to extend it based on your own knowledge of the application and the requirements of the plant. So I said before that we've assembled a really strong set of applications that are familiar to the community that are out there. We've added enough of the secret sauce to make it all work together very, very tightly if it's delivered in a full Emerson context. And, there's different areas. The connectivity strategy is quite important. We find OPC UA MQTT as being, quite critical for this. We're adding a whole set of, 30 some odd drivers into this platform right now so that, regardless of the type of equipment that you have, you can connect to it directly. And that's through a product called Connects, which you can get, independently today, but is now envisioned as part of the standard Edge platform. Grafana is a great tool for doing visualization, and that's a quick way to develop your application. A couple of databases that are in there, I think InfluxDB and MariaDB, also very popular. One is a time series database, and the other is more of a standard SQL database. We find that there's two types of logging that are required to support these little data initiatives. One's more the relational database. You want to log something once a minute, a whole series of tags together at the same time. That's useful for environmental reporting, regulatory reporting, all kinds of applications, or more traditional time series type applications where you're only logging the changes. It's more compressed data, and you can access it very quickly to understand the trends over time. Node-RED and Python are two examples of very powerful tools for building applications. Node-RED, more graphical. There's a great community of people that's out there. It's relatively easy to extend with your own domain logic. We think it's a quite important tool at the edge. Python, honestly, just many people right out of school are very familiar with Python. Super strong programming language, very easy to do machine learning and other complex algorithms. It's a critical part of any edge strategy. And of course, there are other tools that can run in this environment, but these are the ones that we've packaged to make it as strong as possible. And then some standard tools into the functional architecture, which I'll talk about next. So the functional architecture is actually quite important. In today's world, you really want to have things containerized. And so we base it on Docker. We think that's a good choice. Docker is a good way to have a container-based strategy. And then all of the applications that are delivered in the Docker containers. That makes them very easy to manage. So you can manage these applications from a central location across the system. And there's a standard cockpit, which represents the front end, that allows you to remotely configure these applications as required throughout your IoT network. And so that lets you manage the applications, the data. You can remotely access from a central location. You can start and stop the applications, et cetera, in this nice, tight fit embedded environment built on the Docker containers. We use Ubuntu Linux in this environment. Other people have chosen more lockdown versions of Linux. We find that the lockdown versions get you sort of more restricted than you would like to be in order to drive these applications forward. And so we balance the security with the openness in a way that hits that kind of safe point in the middle that allows you the freedom to develop your applications, but in a very secure environment. And so if I show you really where it fits in the architecture, this is also a very interesting chart. And I said that edge is a little bit defined by the user. I mean, edge to one group of people might be sitting right here next to the PLC. And certainly we think about it that way a lot in terms of machine control and the edge applications that are running next to it. But the edge may also be right next to the SCADA system, which is being used to feed data to one of the cloud-based systems. And because this is on a plant network and it's sort of fixed on that network, you really don't want to open it up. Whereas the new generation of edge devices are typically have dual but completely independent networks one to get on the control or the plant network, but a second completely independent to support the cloud-based networks with no way to cross across the two from a security standpoint. Or the edge may actually even be closer to the MES system, either to supply data or to feed data. And so from an architectural standpoint, you really want to think about the edge as something that scales from something close to the equipment down in the bottom left of the chart, all the way through the level 2, level 3 systems, and then feeding the more cloud environments. It's again how your little data-based applications and analytics can feed into your big data strategies, and you get the best of both worlds. Now, I did talk about security. I would like to spend just a minute talking about this. This is a complex problem, especially if you're allowing edge applications to be built on sort of a do-it-yourself type environment on a application that is managed in a distributed environment throughout the plant. And so we found that a critical element of making these best-of-breed applications running together in a secure environment, but still maintain maximum flexibility, is to have an internal virtual network that they're all tied to, and then tightly controlling what can come in and what goes out from that network. And that's on the left-hand side, the internal bus and the external bus. And the reason for doing that is you want the applications to feel safe that if they're connected to the data that's coming up from the equipment, that data is as it originated from the equipment. And when they're communicating with each other, nobody is actually spoofing the data. There's no errant application that's infiltrated into the system. That's a tightly, closed from the standpoint of the network environment for building your applications. And then by having an external data bus with tightly controlled ability to send messages out or receive messages in, you can really verify that the intended external interfaces are the only interfaces that are actually available to that device. And so we really see that the security is quite important in order to make this work as a whole. And if you look at the top of the picture, I show a device. It looks a little bit like a small industrial PC. That is actually a CPL410, which is a IoT-enabled control device. Supports both deterministic control and IoT-based applications in the same box. And you can see the user configurable firewall feeding into the bottom of the box. And that really is the bottom of the box. The networks that are available for the IoT applications are completely separate from the networks that are available that you see facing for the PLC control network. And by doing that, this single device with hypervised technology separating the IoT from the control applications really allows you to participate in the network associated with the IoT applications while simultaneously participating in the control network with no ability for those lines to be crossed across the two. So really interesting application and set of devices. So just to bring all that together, then, we like to think of this next generation of IoT-enabled controllers as the future of automation, in that it supports the traditional inner loop on the left-hand side. That's your deterministic control. It runs the way that you always would expect the PLC to run. But we're recommending these architectures change a little bit in support of what we call the outer loop, which is more edge-enabled and allows this to be more of a software-defined machine. It's a software-defined machine in that you can change the right-hand side based on a more rapid change environment because of the nature of it not doing deterministic control on a set of equipment that's not changing. And the left-hand side as being more oriented around regulatory control of the process and exercising the capabilities of the equipment. And by having these two sides sort of work together, you can change various recipes on the right-hand side based on real-time information and have that impact the left-hand side, the inner loop, based on the way it operates. And it could be as simple as sending a recipe down for the next part that needs to be produced. That's a very common use case. Or it might be something a little more sophisticated in terms of understanding the energy forecast for the next few hours and optimizing when you run high energy consumption applications based on that information. So maybe you're sending a schedule with recommended times to take certain operations through the recipe that goes down to the inner loop. These two are completely separate, as I said. The package and deterministic PLC 61131 is on one side, and the Linux IoT environment is on the second side, and the two work together but independently. So you can see it here in terms of the application. The package application is the IoT-enabled side, and that's what allows us to close the loop, as I discussed earlier, with connecting to not just the control system, but the other devices that are in the network in the bottom dark blue section, and then deliver a set of advanced analytic applications, taking that little data, analyzing it, and providing some insights to the operators. It might be around the air leakage detection that I talked about before. It might be some pressure monitoring. It could be position feedback on the servo or the pneumatics or some other device, because you're trying to understand if maybe you've got more friction than you had to before, so you can proactively do service to get the equipment operating at peak performance. And so it's that combination that I think really gives you the ability to do the deterministic control, connect into additional sensors, run the analytics locally against that little data, serve that little data up to the cloud for the big data initiatives, and then give the operational insights to the operators close to the equipment in order to get a better experience. And I just want to show you two more things to sort of wrap it home in a real world example of how package is used in an example that is actually operating at customer plants. And so this is sort of a functional view of what is happening. And traditionally, you have a piece of equipment, and that piece of equipment is connected into the control and visualization, the traditional SCADA, the traditional PLC or DCS control. It may be, fed by some robotics. There may be some motion that's involved that's managed through the traditional control. This area that's in pink is a very traditional part of the application. So where does the edge control come in? Well, if you see the more light blue oriented applications, and there's smart sensors at the bottom, other intelligent devices, maybe the pneumatics, you can see that the IoT layer, the edge layer, is actually tapping into that additional information, completely bypassing the control system. There's no need to call the OEM that supplied the equipment. There's no need to risk voiding a warranty by opening up that PLC application. You can instrument the device, passively or directly to get this additional information from smart sensors. You can bring it into that edge analytic architecture and store it in these more little data oriented devices. You can run your analytics and get the insights to people via phone, via tablet, via web browser, or other mechanisms. And because it's an edge device, it can connect to both the control and the SCADA system simultaneously. So now you have all of the data that we've had for the last 20 years, plus the rich set of data that's been inaccessible before these edge architectures. And that combination can help you drive significantly better results through your analytic initiatives. And you can see on the left-hand side just some examples of the type of analytics that might be part of this type of application. And so just to take a look at it from a real-world machine standpoint, this is a machine instrumented with an edge controller and set up to display the analytics in real time to the operators and the personnel in the plant. And if you look at the bottom right-hand side, one of the air leak detection sensors that I talked about is in that bottom. Just to the left of that, there's a small window, right-hand side, but the window on the left-hand side, there's a little green light there. In there is a edge controller. It's simultaneously running the IoT application and the control application. So if you think about the blue screens on the top that have the dashboards on it, they're driven by the edge portion of that controller, and then the machine control, obviously driven by the PLC side of that edge controller itself. And this is what I would call a modern smart machine. It monitors its own health, through the analytics. It reports on its own efficiency, especially if it's got something like an OEE application running. And it is able to call for help through SMS, through email, through text, through other mechanisms if there is a problem that's emerging that it wants to make sure somebody gets involved in. So, if you think about a modern machine, this is sort of a good view of what one might look like. And it tells you what's possible in today's world, the art of the possible. Much better uptime, much better efficiency, and interoperable with other equipment and the data, of course, through an edge architecture is available for further analysis. So, I encourage you to think about where you are on the journey. Do you have some islanded automation like most of us? Do you have primarily a connected enterprise? Are you starting to think about enhanced connectivity and analysis to start your insights-driven journey? Or are you on that extreme end where all of your operators are already operating based on insights that are coming to them and recommending the action to them? Most people really fit in that connected plant environment, and really would like to get to the enhanced connectivity and analytics phase. For that, you need the new edge architectures. I think that's where Emerson can help you. So from the standpoint of the big data, little data, start close to the source. Think about the little data, what you can get your arms around, understand what the known problems are. We can get to known solutions from that known problem. Even if we don't know what the solution is, the insights that you'll get from the little data analysis will lead you towards those known solutions. Choose a partner and a platform that scales with your business, somebody that's going through the journey themselves and understands this application, that has some lead customers in the environment. And keep both of your options open, the big data and the little data, but learn through the little data approach, get that going quickly and soon. And as that scales, you'll find yourself in a big data environment naturally without all of the risk of gathering and storing that data speculatively without actually knowing how you're going to use it. So it's the best combination, I think, from both worlds. So with that, that's the end of the presentation. I think we would like to go to Q&A. Gary, maybe I turn it back over to you.
Sounds great. Thanks so much, Rich. So now we are going to address your questions. Derek, there's actually going to be somebody else joining us. So Rich will be joined by Derek Thomas. Derek Thomas is the Vice President of Marketing and Strategy for Emerson's Machine Automation Solutions business, which provides innovative industrial automation and control solutions that serve the global factory automation, process automation, and industrial machinery market. Derek holds an MBA in brand management from Washington University in St. Louis and a Bachelor of Science in Mechanical Engineering from Purdue University. So if you have questions for these gentlemen, just simply type your questions for them in the Ask a Question box on your screen, and we'll get to as many as time allows. Questions that we don't get to today will be posted online with the archive version of this webcast. Also, remember to download a certificate of completion and a copy of this presentation. Use the Event Resources tab on the left side of your screen. All right, gentlemen, if you guys are ready, let's get started with some questions. So is the little data approach similar to a pilot project, or is this approach something that can be scaled once the first project is complete?
Yeah, so I think that's a very good question. I would say maybe it's one step beyond a pilot project. It's an important first step, but you really want to have a good understanding of a problem that you're trying to solve. You want to start with that local machine is the best way to do it. Get some experience with it. I think it's a little bit different than a pilot in that you want to, as you learn, you want to keep it in production and then maybe scale from there.
Terrific. So what is the current status of edge IoT in industrial and then also distributed learning at the IoT edge? And can it help?
Yeah, I think this is a great question. Honestly, we're at the very early stages. Many people that I talk to sort of know they need to do something with IoT. They're committed to it. They're not sure exactly where to get started, and they're not sure how to define the benefits that they're going to get from it. And so I think this is an area that having some experience with, having some people that have done it before, that have seen what the leading OEMs and manufacturers are doing, can really help those that are just getting started on their journey. It's not intuitively obvious because for the last 20 years, we've done it a certain way. And now all of a sudden, there's this wealth of information that wasn't previously accessible. A lot of people aren't even thinking about or know how to tap into that information. And that's an area that we can definitely help. So I would say we're at the very, very early stages, but without question, it can help and it can drive competitive differentiation and better efficiency and sustainability.
Sounds good. So in slide 23, there are two sets of sensors, blue and pink boxes. Does that mean that you have to have duplicated sensors?
Okay, I see the question here. You don't have to have duplicated sensors per se, but you might have two sensors of the same type that are providing you information from two separate parts of the process. And I have to go back and look at the specifics of slide 23. But no, you definitely do not need to duplicate sensors. If the sensor is plugged into the control system, you can normally use open standards to get the data out of it. But if it's not part of the control system and you added that sensor standalone, this new edge architecture lets you tap into it without ever opening up the control system. And that's really what drives a substantial change in that you can move so much faster to get additional analytics.
Yeah, Rich, and I think the thing I would add to that is exactly just building on what you said, is that as machines are becoming more and more advanced, you're adding those pervasive sensing types of sensors like airflow sensors on the pneumatic system or other data capture elements that aren't critical to the logic of how a machine works, but they can give you tremendous insight. And sensors are becoming less and less expensive. So you're pulling that data in, whether it's over Ethernet or IO link, and it really richens up the information that you get out of that machine without necessarily clogging up the main machine network or the processing power.
Terrific. So we'll keep moving on here. With so many different data types and formats available from so many different sources, how can someone determine where to start and what kind of data should they start with?
Another good question. I think you start with the data that you're familiar with. Usually that's some type of process data, especially if you're down at the edge, because you're really talking about data that's collected from machines and sensors. Sometimes you don't know where those correlations are going to be, so you look at what's available. Sometimes the machine is having a certain type of problem, and you don't have enough information to troubleshoot it, so you add instrumentation to the machine to be able to get insights relative to that problem. You bring that into your edge device, and a lot of times, just through simple trends, events, alarms, other mechanisms, you can very quickly start to understand, oh, I see what's happening. It's traveling 2 millimeters less every month, and so as a result, I'm producing more quality problems than I expect, right? So I think you start with the data with the problems you're trying to solve. You assess whether you have the information to be able to understand the problem, and if not, you start to instrument the equipment to get that data.
So another one here, would you consider product quality and traceability more of a little data or a big data approach?
I think it's a little bit of both. If you're thinking about it in terms of full traceability and genealogy across an entire plant, especially a high-speed plant in consumer packaged goods or some industry like that, it's really more of a bigger data problem that we're talking about here as edge analytics. It's sort of in between because a lot of times that's done with data marts, data warehouse type initiatives. But as soon as you take that across multiple plants, no question, that's a big data problem. I think as you're closer to the machine and you just want to know, all right, well, who was the operator and what machine was it and what were the conditions at the time we made this part with this defect, that can be solved with a little data environment and simple OEE relatively quickly. So there's a little bit of both depending on the scale of your application.
Makes sense. Next question here is, what's the main difference between expert systems and machine learning?
Yeah, so expert systems have been around for a long time. I think people are fairly familiar with them. Often they're rule-based, and they're trying to understand, I'm going to say the best decision, but often they're set up to pick the least bad decision. It's kind of the the state of the art, but they're helping you to make a decision based on available information that has been plugged into the system. Usually it's manually or somehow fed into the system. Machine learning is a little bit different. The two main use cases, at least that we get involved with from the edge, are often around vision-based analytics, and that's often used to recognize something. So by having a video capture a piece of equipment through machine learning, you can learn to recognize that equipment. And then if you have an augmented reality type application at the edge, as an operator walks around hands-free, but with the augmented reality equipment, that equipment becomes recognizable. And then you can use standard edge techniques to be able to display key KPIs and additional information to that operator who's on the go. That's more of a machine learning application using vision. The second place where we see machine learning used quite extensively is around models of equipment. And this is actually good news for the discrete industry, because unlike the process industry with large rotating equipment, where it's been relatively easy to do predictive diagnostics, that has been very, very challenging in more of the discrete environment, because each machine is somewhat unique and often tailored to the customer's manufacturing process. Machine learning provides an environment now where you can learn based on the way the machine is operated over a regular period of time, produce models, potentially in a cloud, potentially in a server room somewhere, that describe good behavior for that machine, and then compare good behavior to current behavior. And if there is an anomaly, start to surface those and potentially predict some future failure that could happen. And so machine learning, I think, is at the very beginning. Expert systems have been around, and we'll see machine learning become ubiquitous across our industry, over the coming years, is my personal view.
So we have time for just a few more questions here. So let's go with, do we need to have one place for data to be stored? And what's the advantage of having one place versus multiple places?
Yeah, I think data is going to be stored in multiple places, to be honest with you. The whole little data approach is based on that premise. You store the data local to the problem you're trying to solve, little data environments on edge devices distributed throughout the plant. But you need good connectivity to the central storage locations. You probably are not pulling all of the high fidelity data up from the edge into those centralized storage areas. It's probably either samples or maybe results based on the analytics that are run. But some subset, based on the application need, is going to travel to those. I think, some people may have local plant-based centralized storage, but then they may use cloud-based environments to store information across multiple plants. And so really, I think data is going to continue to be distributed and close to the point of use and near, in an environment that's best suited for the tools that are available to analyze that type of problem.
Great. Our next question here is, what are the differences between edge devices and other data acquisition techniques?
The data acquisition is sort of a general term, and an edge device has a data acquisition technique built into it. So I would say a data acquisition technique is a component of an edge device. What differentiates the edge device is, for example, data routing. The ability to connect something in on one protocol and without any programming or any additional scripting or anything, you can route that data to another place. So bring it in from an industrial device and immediately route it to MQTT. That's one difference. The second difference is the incorporation of advanced analytic tools, like we talked about Grafana and Node-RED and Python and others that are part of the edge device, to take that data once it's been acquired, analyze it, and provide some insights to customers. Incorporation of dashboarding tools so that that information can be made visible to operators. So I would say data collection, data acquisition is just one component of an edge device.
So you've been doing this for a while now. What questions do you hear most often from those who are starting out with new projects?
I think that most people are trying to they know they need IIoT. They see their competitors doing it. They want to have an edge initiative. They need help getting started to say what area will bring them the best benefit, what type of architecture should they start to deploy, and what's the first couple of problems that they can solve to justify to themselves and to leadership within the company that this is valuable to spend time and money on in order to get good at. And I would say most of the people that we talk to Once we help them through that hurdle, then they just sort of get it. The light bulb goes off and they're off and running.
Thank you to everyone for all the great questions. And thanks again to our speakers, Richard Carpenter and Derek Thomas, for sharing their time and expertise. I'd also like to extend special thanks to our sponsor, Emerson, for sponsoring today's event. And now that we're just about done, although we're not quite done, we still want to hear how we did. So the exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve our webcast going forward. Finally, on behalf of Control Engineering and Emerson, I'd like to thank you for attending. This concludes our webcast. Thanks for joining us, and goodbye.